Okay, welcome everybody to this discussion on solid hexahedral elements for finite element analysis. Let's go ahead and get started. So the first thing we want to take a look at is how the isoparametric hexahedral element is very similar to our 2D isoparametric quadrilateral element. So first is our 2D isoparametric quadrilateral element. We can go ahead and draw the four nodes. We have our natural coordinates, xi and eta. We can then start drawing our 3D isoparametric hexahedral element. We'll start with that same or very similar four node type of element like we have over here. We'll just draw another one of those on top of it. We'll still draw our natural coordinates, xi and eta. We'll draw a third natural coordinate, zeta, and then we'll go ahead and connect it. So very similar to our 2D isoparametric quadrilateral, we just have one additional natural coordinate direction because it's in 3 dimensions instead of 2. All right, so next is investigating what types of degrees of freedom each node has in the hexahedral element, specifically what types of stiffness is present at each node. And just like our 2D isoparametric quadrilateral element, since it is a 2D element, in 2D space, no rotational stiffness is necessary. And so that means that there is only translational stiffness at each node. Similarly, if we look at our 3D isoparametric hexahedral element, it is a 3D element in 3D space. And so for that reason, no rotational stiffness is necessary. And we just have 3 degrees of freedom of stiffness at each node. So we have a total of 8 degrees of freedom for our isoparametric quadrilateral element, and we have a total of 24 degrees of freedom for our 3D isoparametric hexahedral element. Okay, so taking a look at our displacement function, it is composed of shape functions just like our 2D isoparametric quadrilateral element. So in the 2D isoparametric quadrilateral element, we may remember equations like this for our horizontal displacement in terms of our shape functions and their corresponding nodal displacements. It's very similar form for our vertical displacement. And if we go ahead and look at our 3D version, the only thing that really changes is that we have 8 nodes instead of 4. And so instead of just summing 4 different displacements, we have to sum 8 different displacements and with their corresponding shape function evaluated well at whatever coordinates we have here for xi, eta, and zeta. Very similar form here for our vertical displacement, or pardon me, I guess I should say our y direction displacement. It's not a 2D anymore, so we have our x direction displacement, y direction displacement, and our z direction displacement. Okay, very good. Let's go ahead and look a little bit more deeply into our shape functions, and just like the 2D isoparametric quadrilateral, they are written in terms of the natural coordinates. So there is our hexahedral element with the natural coordinates, and we'll go ahead and start with our shape function for node 1 right here, and we'll start with 1 minus xi because at negative xi, right, we should expect it to be equal to 1, and if we have plus xi anywhere else, we want the shape function to be 0. Remember, the property of the shape function is it is equal to 1 at its corresponding node, and it's equal to 0 everywhere else. So similarly, 1 minus eta, because anywhere that eta is 1, we would like our shape function to be 0. Finally, the last one is 1 minus zeta, because we'd like anywhere where zeta is equal 1, that whole top surface, we would like that to be 0 too. Okay, so that really only leaves our position at node 1 to be non-zero, but of course, if we have xi equals negative 1, eta equals negative 1, pardon me, and zeta equals negative 1, well, we'd have 2 times 2 times 2, which is 8, so we got to go ahead and divide by 8 to make sure that our shape function is equal to 1 at node 1. Okay, so we have very similar forms for node 2, node 3, node 4, and we can go ahead and say that the shape functions for 5 through 8 are exactly the same as 1 through 4. The only difference is we have 1 plus zeta instead of 1 minus zeta. All right, so those are our shape functions for the hexahedral element, specifically the linear 8-node hexahedral element. All right, so now let's take a look at the Jacobian matrix. So in 2D, we had a 2x2 Jacobian matrix because we were relating 2 dimensions in physical coordinates, x, y, with our 2 natural coordinates. Well, now we're going to ahead and take a look at our 3 natural coordinates, xi, eta, and zeta, and we're going to go ahead and relate this to our physical coordinates, x, y, and z. And so just sort of showing the chain rule in effect here, right? If I wanted to find the derivative of my first shape function with respect to xi, I could go ahead and say it's the derivative of x with respect to xi multiplied by the derivative of my same shape function with respect to x. And we just go ahead and do the same thing for y and z. All right, we'll go ahead and populate the rest of this Jacobian matrix. There we go. And as a reminder, when we solve for each portion in this Jacobian matrix, right, the derivative of x with respect to xi, for example, it is really the derivative of each of our shape functions with respect to whatever our natural coordinate is here, right? We have xi down here, right? Okay, multiplied by its corresponding physical coordinate, right? Just like our displacement functions that we showed earlier can be written in terms of our shape functions and nodal displacements, we can also do that for our physical coordinates. All right, let's go ahead and move on. We have the stiffness matrix equation for hexahedral elements. We want to go ahead and show that it's very similar in form to our planar element. Notice that instead of having a thickness here, we just have another integral because it's not 2 dimensions, it's 3. We can't assume that it's constant throughout that 3rd dimension, so we need to integrate throughout that 3rd dimension instead. We have the determinant of our Jacobian matrix. We talked about how that's now a 3x3, mapping 3 natural coordinates to 3 physical coordinates. We have our constitutive matrix, which will now be a 6x6, and where in 2 dimensions we had to assume plane stress, plane strain. Now we don't have to assume that. We have a full 6x6 constitutive matrix that will be implying there, and now we have our strain displacement matrices over there. All right, so very similar in form. Go ahead and take a look at how we have now 6 types of stress and strain compared to just 3 like we did in our planar elements. So this is sort of a precursor to when we talk about the constitutive matrix. Here's a 3D stress element. First thing we can take a look at is our normal stresses, and we can draw a relationship between our normal stresses and our normal strain. And of course, due to Poisson's ratio, we have a coupled relationship here. All right, we'll go ahead and now draw our shear stresses on that stress element. And shear stress is much more simple. There's no coupled relationship. Each shear stress is related directly with its corresponding shear strain according to the shear modulus. And there's the relationship we have between our shear modulus, elastic modulus, and Poisson's ratio. So we're going to go ahead and combine all that into our constitutive matrix equation, which is now a 6x6 equation. And we're going to show the isotropic version of this. Composites or anisotropic would be much more involved, so we'll just keep it simple for now. And all we're doing here is we're just applying that 3x3 coupled relationship we saw for our normal stresses and normal strains, and then the direct relationship we have here, just making a substitution for our shear modulus with similar terms that we have here with the elastic modulus and Poisson's ratio. Okay. So we'll move on to eventually talking about our strain displacement matrix, but as a precursor, we're going to talk about our strain relationship to shape functions and nodal displacements. All right, we have our strain in the x direction, same formula as what we had for our 2D isoparametric quadrilateral, just now we have 8 nodes instead of 4. Y, same thing. Same type of equation here, just have 8 nodes instead of 4. We have a 3rd dimension now, So we'll go ahead and have an equation for the normal strain in the z direction, and we'll go ahead and draw relationships now also for our shear strains. This relationship here is exactly the same as we also used in our 2D isoparametric quadrilateral elements, but now we have two additional shear strains that are possible in our YZ plane and also our XZ planes. All right, so we're writing all these out to eventually show the form of our 6 by 24 strain displacement matrix. Wow, it got big, but remember we have 24 degrees of freedom now, and we have 6 types of strain. Starting with a strain, we'll go ahead and write that vector over there. Our 24 total degrees of freedom. I do not have enough space throughout this, so we are going to just draw node 1 degrees of freedom, the 3 degrees of freedom for node 1, and the 3 degrees of freedom for node 8, and some dot dot dots to fill in the rest of the gaps. All right, so all we're doing now is we're just kind of populating this matrix according to the equations that we had on the previous slide to give an idea of what this strain displacement matrix would look like. All right, great. Now, of course, one thing similar to the difficulty we have with our 2D isoparametric quadrilateral element is recognizing that our shape functions are not in terms of x, y, and z. Remember, they are in terms of our natural coordinates. So that'd be xi, eta, and zeta. And so for that reason, we need to go back to our friend, the Jacobian matrix. There it is. I got a little bit ahead of myself. There it is. Need the Jacobian matrix to find the derivative with respect to our physical coordinates. And so we can take the equation that we saw a few slides earlier with the Jacobian matrix, and we can draw a relationship between these derivatives with respect to our physical coordinates and these derivatives of the shape functions with respect to the natural coordinates, which we can find relatively easily. And we can draw that relationship with the inverse of our Jacobian matrix. All right. Well, now we've got our everything I think defined for our stiffness matrix equation, but now we got to talk about how to solve it. And just like the difficulty we had with our 2D isoparametric quadrilateral, we have that same difficulty in 3 dimensions. It'd be a pain to really try to integrate it. So we use Gauss quadrature to do that much more simply by creating 8 Gauss points throughout. It's 2 by 2 by 2, 2 in the xi direction, 2 in the eta direction, 2 in the zeta direction, 8 total Gauss points. Kind of have a little Gauss point cube there in the middle. And so we can go ahead and take that original integral equation that we have for our stiffness matrix for the isoparametric hexahedral element, and we go ahead and replace these integrals with summations, and we take the integrand and we go ahead and evaluate it at each one of those 8 Gauss points. And all we do is we just evaluate, just as it says here, we just evaluate our strain displacement matrix and our Jacobian matrix at those Gauss points. And since we're using 2-point Gauss quadrature, I mean it's 2-point Gauss quadrature in 3 dimensions, which is why we have 8 Gauss points, but really it's 2-point Gauss quadrature, and so that means that these weighting factors are just 1.0. All right, so we can use Gauss quadrature to fully develop our stiffness matrix, and let's say we go ahead and run through the whole FEA process. We got our nodal displacements. We're now going to try to figure out what our stresses are. The first thing they do is they evaluate the stress at the Gauss integration points, and the reason they do that is because that's where we already have our strain displacement matrix evaluated or figured out. We already have it solved for it. We needed it in order to figure out our stiffness matrix for the element. So we can go ahead and do that by just taking our stress vector. Remember, there's 6 types of stresses that are available now for this 3D element. And we say it's equal to our constitutive matrix multiplied by our strain displacement matrix multiplied by our vector of displacements that correspond to the element. So it's 24 by 1, right? We will have 8 nodes, and each node has 3 degrees of freedom. And remember that our strain displacement matrix is 6 by 24, and our constitutive matrix is a 6 by 6. All right, so once we have the stresses at the Gauss points, we go ahead and extrapolate them to the nodes, which is usually what we'll see reported. So here's our hexahedral element. We'll draw our Gauss points again, draw our nodes, and just write a quick equation saying that if we want to find the stress at node I, remember this is a 6x1 vector, we can say that it's equal to the sum of each of our shape functions. Specifically, it's a Gauss shape function. Really, it's the kind of the same thing as our regular shape functions for the element. We just use our Gauss coordinates here. Okay, we'll talk about that in just a second there. This is our stress at the Gauss point, J, right? So we just sum it through each of these Gauss points, and this shape function would correspond to each one of these Gauss points, but it would be evaluated at the coordinates corresponding to this node. All right, a quick note about these Gauss coordinates. They are the same directions as our regular natural coordinates, it's just a different scale. So we're sort of assuming that this little purple box that we have here where the Gauss points are, we're assuming that the corners of that box are at plus minus 1 in each of those coordinates, and then therefore the nodes using the Gauss coordinates would be at plus minus square root 3. All right, so in summary, for our linear 8-node hexahedral element, what we have is, well, first we have our element. Okay, there it is. First we have a few benefits. The first benefit is it creates a nice ordered mesh. It's pretty to look at, and it was easy to code when you had to code your actual mesh by yourself before GUIs really got good. It was nice that way. It converges much more quickly than the 4-node linear tetrahedral elements. As a reminder, please don't use those. They're pretty bad. So don't use those elements. It does converge much more quickly than those. All right, that said, there are some cautions that we have. And so some of the possible issues you might have. First is, well, you can't really mesh difficult geometry. In order to mesh difficult geometry with hexahedral elements, you would have to do one of two things. You'd have to be very careful at subdividing or just use tetrahedrals. Not linear tetrahedrals, you would use quadratic tetrahedrals. All right, so that would not be your 4-node tetrahedral, right? I think it's about a 10-node. So that's the first concern. Second, just like those linear isoparametric quadrilateral elements in 2D space, shear locking is still a thing. And so here we have an original element, and I'm just looking at the 2D profile of this, right? We apply a bending moment to that element. It creates this trapezoid type shape. We notice that the internal angles of this trapezoid shape are no longer 90 degrees. We know in pure bending, there would be no shear. But since these angles change, that means that some artificial shear strain is developed. That means artificial shear stress is developed, which means we have a bit of a problem. Okay, so the solution is use quadratic formulation. And for the hexahedral element, instead of using the 8-node hexahedral element, you would use the 20-node hexahedral element. All right, and the last concern is connecting to other element types. Let's go ahead and draw our hexahedral element there. We'll go ahead and draw a plate element. Now, plate elements or shell elements do have rotational stiffness. Solid elements do not. And so as a result, this intersection kind of resembles a hinge, right? The shell element is expecting rotational stiffness at this intersection with that solid element, and it's not there. And so the solution would be embedding an element. So with this shell element, we could just embed another shell element right here on the surface of that hexahedral element, and this embedded element would retain that rotational stiffness. And you could do something very similar with a beam. If you had a beam connecting to a point over here, you could just embed a beam element there, and that would retain that rotational stiffness. All right, so that's the benefits and the possible concerns with these types of elements. Let's go ahead and get on to our reflection questions. The first reflection question is, why is rotational stiffness absent in solid elements? Okay, related to that, what concern exists when connecting two elements that do have rotational stiffness? Boy, we just talked about that. Okay, and finally, how does that stiffness matrix equation for an isoparametric quadrilateral element change when we use it for an isoparametric hexahedral element? And that concludes our discussion on isoparametric hexahedral elements.